Değerli katılımcılar, ikinci oturuma hoş geldiniz. Bu oturumu değerli meslektaşım Çin'den aramıza katılan Deuckhang ile birlikte sunacağız. Deuckhang Sichuan Üniversitesi'nde çalışıyor. Pek çok idari görevi var. Oradaki departmanın başkanı olarak görev yapıyor. Aynı anda Çin'deki ve uluslararası bazı üniversitelerde de idari görevleri var. Yapı ve deprem mühendisliğinin değişik konularına odaklanıyor. Prefabrikasyon, yerine dökme yapılar, özellikle enerji yutan cihazlar, sismik izolatör vesaire gibi Çin'de de bu alanda çok tanınan arkadaşlarımızdan bir tanesi. Şimdi hemen süreyi uygun kullanmak için konuşmacılara geçiyorum. 4 tane konuşmacımız var. İlk konuşmacımız Deuckhang, Güney Kore'den 30 dakikalık bir açılış konuşması yapacak bu oturumda. Ben biraz bilgi vermek istiyorum. Deuckhang, Güney Kore'nin Suwon şehrindeki SKKU İnşaat Mühendisliği, Mimarlık ve Peyzaj Mimarlığı Fakültesi'nde doçent olarak yeni görevine başlayacaktır. Kendisi şu anda Chungbuk Ulusal Üniversitesi'nde doçent olarak görev yapmaktadır. Daha önce Kazakistan'daki Nazarbayev Üniversitesi'nde doktor öğretim üyesi ve Illinois Üniversitesi'nde Amerika Birleşik Devletleri'nde Urbana'da doktora sonrası araştırmacı olarak çalışmıştır. Profesör Lee, ASCE komitesi 550 yani prefabrik beton yapılar ve ACI'nin alt komitelerinde 445E kesme ve burulma ve 445F kesme ve burulma arayüz kesmesi gibi birimlerinde oy hakkına sahip asil üyedir. Bunlar önemli komiteler. Araştırma alanları arasında yapısal betonun kesme davranışı ile prefabrik ve öngörülmeli beton binaların deprem analizi ve tasarımı yer almaktadır. Professor Lee, yes, you have 30 minutes.
Thank you for your introduction. I prepared one single slide for my introduction for you. First of all, thank you for having me today. I'm really happy to visit Turkey as the brother country of South Korea. All the Koreans actually remember your help during our hard time in the 1950 to 1955. Thank you. All right. This is me, and I cannot see my screen up there. I'm currently working at Chungbuk National University, and I'm the editor-in-chief of the Earthquake and Structure, published in the Techno Press journal. Maybe many Turkish professors know structural engineering mechanics. And then I'm an ACI member and director of a lot of institutes, Earthquake Engineering, Society of Korea, and then K Prekast Concrete, and other things, and I'm an active member of ACI 550, the precast concrete structure, and also actively working on the structural concrete journal in FIB journal. So that's alright, and then you can scan it, this one. No one have an interest, but yeah, for your reference, you can scan this one, and you can visit my website for your more details. Let me start with the industry, the fabrication in South Korea. This one is actually like Amazon. Amazon is a logistic building, typically made of precast concrete. You can see this is a high-rise building. The building story number is maybe over 20 or 30, but this 5-story logistic building height is comparable with high-rise residential building. It's very, very impressive. 100% precast concrete because high load we can sustain by the pre-tension, pre-stress concrete members. And also the building height is key issue of the application of the precast concrete because the traditional formwork is impossible to build this large height of the building. And this is semiconductor factory. It's like a Samsung. It's a SK Hynix building. This story also just 6, right? But you can see the high-rise apartment is smaller than that. That means the precast concrete multi-story building, just not the floor number, is the building height. And larger height, longer span, the solution is inevitably precast concrete. And this is an industrial buildings up there. This is the PACO system today. My topic is PACO. A lot of the plant, especially energy plant, is built of the multi-story, multiple, the column. You can see that. And then this is, yeah, thank you. Kind of the Costco or some retailing market also made of the precast concrete. And definitely parking structure on the ground, 100% made of precast concrete in South Korea. And you can see which one is better. The left side and right side is a twin building. The government pushed this development of this building, and there was a competition last year. You can see, okay, the left side is the bearing wall system for the large seismic load there. This is typical shear system made of reinforced concrete. And this one is precast concrete twin building. So much faster you can see. There's a very slow in the reinforced concrete, monolithic connection. Traditional one is slow, but you can see we can accelerating the construction speed by using the precast concrete, especially my topic today is a dry connection without cast in place concrete. Right? So final view is something like that. We cannot recognize which is different. So this is a fully reinforced concrete. One is a fully the precast concrete. We can see on the quality control is much better. Now we can build a precast multi-story apartment, easy peasy. Right? Okay, this is a video. I will show you the mock-up test constructed by the Hyundai Construction. Is one of the best country. We utilize the hollow slab and then a wide column by using the column shoe made of the PACO system. And inside the core wall is made of typical reinforced concrete. All the moment frame system is 100% the precast concrete. This is just a 3 or 5 story building, but we design. Our target is actually 40-story building. This is just a mock-up test. And you can see the crane from the China, all right? Kaoshan, yeah, crane from China, all right? Yeah, it's yeah, no one, yeah, smile. It's very serious today, okay? Let me go. Yeah, that guy is the professionals in America, and finally we have happy news. I hope that the Turkish industry follow the American practice. That means ACI officially accept the precast concrete as an official structural system. That means ACI 318, the building code for the structural concrete, that is for the reinforced concrete. But the ACI 319 is issued now, and that is for the precast concrete. So we are very happy as a precaster. Right now, we have our own code for the precast concrete. So 319 is there. This is a 318. Before 2025, we are just included in the 318 subcommittee. But now we are independent right there. So 319 is precast concrete for the only code, and 320 for the post-tension. So post-tension independent, precast independent, it's really freedom, okay? Yeah, so Korea saying we have the only for the precast code now, so we have to follow the seismic design by using this one. Our code is also similar with the American practice, so it's happy. So we can collaborate with the Turkish industry because almost the same environment we have. Okay, let me just skip the brief introduction of the ACI 319 system. So we have the emulative system and semi-emulative system and non-emulative system. So many guys have a misunderstanding about the dry connection, especially PACO is joint precast. No, it's an emulative system. Today I'm going to show you how we can show the emulative performance. That means a comparable performance with the monolithic connection. Okay, this is a brief summary of the ACI jointed and emulative connection design. As you can see, this one is our target. So the ductile connection system allowed in ACI that doesn't allow the mechanical splice within the plastic hinge. But the strong connection, that means based on the overstrength design, we can locate it, the splice sleeve or any mechanical connector, any location of the beam and column. So that is just you can find this overstrength design. Let me skip this one. So this is some kind of unbonded system. That is, unbonded system always make an elastic range, so we can take some advantage of the self-centering, but there is no energy dissipation. But our code, you can see, the code requires energy dissipation. This is a good example. The left side and right side, the same column, foundation connection. But left side, the mechanical splice is located in the base. The splice performance is really good. There is no residual slip. The right side is, this is a screw is not that good, or grouting is not, grouting performance is bad, quality is bad. In this case, you can see, we remove the load, there is a residual slip. So the precast concrete, 100% rely on the mechanical connector. But connector performance is not good. That means cracking is concentrated in one single section. That means it lost the strength. Stiffness, mostly important thing is it lost energy dissipation. That means we cannot utilize it in the code practice. But the mechanical splice is the same. The dotted line is RC, typical reinforced concrete, and the red one is a precast concrete. Much better performance sometimes we can obtain because a mechanical splice, if the joint have no slip, its local stiffness is higher than the typical, the continuous reinforcement, so usually higher performance we can expect. All right, so we target today is an emulated performance, and maybe there is, wet connector and dry connector. Let me focus today on dry connector. The dry connector is really important to facilitate the construction speed in the field. And the emulated design behind the ACI code and Korean design code is emulated means not equal. The emulated performance means equal performance or compatible performance. So it's a shape and the detail is different, but its final performance, especially seismic performance, have to be same. So how we can do this? It's a strong connection design. I addressed it, the PECO system here. Anyway, there's column shoe, and this reinforcement is blue. The blue is expressed in this chain. So chain subject to tension, if we intentionally lower strength provide to the here, and then other things is a brittle link, we can intentionally increase its strength. In that case, yielding is inevitably occur only the blue. That means here connection, the foundation interface, we can provide a large diameter reinforcement. And then in here plastic zone, we can provide a very nice reinforcement there, and yielding inevitably occur always here. That means we can control the plastic hinge location always there. And then if those kind of things, right, for example, shear strength in here is rely on the interface shear, so-called shear friction. The shear friction strength is always higher than the shear strength of the column section because a large diameter reinforcement is across the foundation interface. So the yielding is occur here, and other guys always protect by the overstrength. We combine those two reinforcements finally, we can obtain the clear yielding location and also clear ductility and energy dissipation. So wall and the beam column and everything, we can do same principle. So it's a very, very important concept, the overstrength design. And let me show you this, some demonstration of the mock-up test conducted by Korea government. Korean government have a big concern about the mechanical grouting sleeve because the grouting sleeve quality control, if the quality control is okay, the performance is really good. But sometimes in Korea, the labor workers have no understanding of the grouting process. So let me show you some, okay, it's a long video. So we intentionally make the grout sleeve by using the 3D printing the crystal, and then we can remove the pressure, so always there is an inevitable defects occur in the top of the grout sleeve. So you can see if the grout sleeve, the performance is good and quality control is good, like Japan or Europe, on America may be good. But in South Korea, Korean workers have some kind of issue. In this case, you can see we cannot get a full tensile strength. It's yielding, but no ductility. So it have some kind of issue. So we need some important sum measure, the countermeasure, and you can see that there is an eccentricity between the top reinforcement and bottom reinforcement. We cannot avoid that one. So in this case, you can see the stiffness is decreased in this case. Strength is okay, but stiffness is a little bit decreased. That is not good for the seismic connection. So we conducted some tests, mechanical splice here by using the laser scanner. And then you can see if the grouting is good, we can obtain the best performance for the grouting sleeve. But as you can see the previous slide, grouting is bad or bad workability of the grout itself. The grout filling process always have some issue. So we need some kind of inspection method or something like that. So we don't want any kind of this kind of stressful condition in site. As you can see in the actual construction site, we have a lot of jobs. But someone have to inspect all the mechanical splice. That means it's very stressful. So all the accident in South Korea, even America, happen due to the mechanical splice, not the completion. During the construction, it happened. So in Korea, the government pushed the engineer, protect all the labor force safe under and during construction. That is key. So important thing is that last year we have 6 disasters during construction, not earthquake. Because of precast, right, always rely on some prop support, temporary support. We cannot control everything. So you can see here splice, grouting issue, and grouting issue, and even full grout. The strength is not reaches target strength. These kind of things that happen, seriously. So you can see in construction site, you can see that there is a prop support. So the first generation of the precast concrete, so-called emulative connection, you can see the void space of the panel zone, the key, the component of the seismic connection. But if you utilize this kind of connection detail, we cannot reduce the construction time because we have to wait. We want to install top column, but we have to pour the concrete in the casting place here. That means we need to wait. But the trend in South Korea is a solid panel zone. The panel zone itself already prefabricated in the factory. That means the large diameter reinforcement already pre-installed in the precast column. So the top of column just connected without any waiting, so that we can facilitating the construction speed. And then we can connect to 4 corner reinforcement by using the dry connector. That means we can obtain minimum safety without any prop support or any kind of temporary scaffolding. So yeah, this is our site now, and we want to go like this without prop support, without scaffolding. So this is key mechanism. We can obtain the dry connector and solid panel zone. We can get 2. The first one is construction speed, and second one is erection safety. All right, so this is just a typical, let me go. I show you. So the seismic design behind, we are just talking about the ductility, but behind our code, especially American code, you can see the energy dissipation is a key factor for the response modification factor. So not even there is ductility, no energy dissipation. That means we have to use a low response modification factor. The higher response modification means the higher energy dissipation. So energy dissipation is key, so we have to make it yielding. For example, here, the DR2 have a large energy cycle, and DR3 has a half of that cycle, but its ductility is the same. So ductility same, energy dissipation low. According to our code, we just follow the same response modification factor. But important thing is energy dissipation behind the code, so we need that kind of energy dissipation. So we need to test the PECO system and whatever the new system, we have to test and demonstrate its actual performance, so-called emulative performance. So left side is an intermediate moment connection utilized frequently in low to intermediate seismicity region like Korea. And then light size maybe high seismic risk region like a strong connection, special seismic design code right here. So the only one, the long story short, yeah, you can see the left side of the mechanical splice, the reinforcement size is same. That means it's intermediate. Yeah, overly simplified, I know. Yeah, I'm ready to accept your criticism, but for your better understanding, okay? So right side is a large diameter. So the key to successful application of the mechanical splice is the connect the different diameter of reinforcement according to ACI 318 and 319, the strong connection design. So the PACO here, we gonna start with the 10-minute time attack. You can see there will be the clock there. So here it started already 5 minutes we used, right? Yeah. So per column here is a high-rise building, RC core, and the column there, only 2. The workers up there, yeah. We don't need to control very tightly, just the snug tightening in the steel structure, right? So snug tightening is okay, and then we can make an erection later, and then we can install the beam. That is our target, all right? Okay. So it's another project, let me skip it. So our test is here. So left side is the full dry connector. That means all full reinforcement in the corner, we utilize a beam shoe made of the PACO system. And right side is a help piece system. Oh, thank you. Yeah. Help piece system, so beam has a bottom reinforcement is key for the positive moment. In this case, we utilize the beam shoe, but the top of the concrete, we anyway, the cast in place concrete is required because to make a composite slab. So CIP concrete topping is required. So the top is just a typical, so it's the mechanical connector. So we can do right this way. That means this one is much safer, I think, during the construction. But this one also safer because the 2 reinforcement already fixed right there. And then we can take a minimum advantage of the dry connector. And then we can protect our economical aspect. So they minimize the PACO system, and then we can utilize that one. And also the column here, all the reinforcement is connected by the dry connector. And second specimen, we utilize the splice sleeve. Actually, it's not the splice sleeve. It's a Korean style splice sleeve. Don't misunderstand. The Japanese one is much better, maybe. So the Korean one is a splice. It's another type of splice sleeve. Anyway, grouted sleeve. And corner 4 is utilize a dry connector. That means we can obtain some kind of stability during the construction. Okay, so full scale test right there, and left side and right side, we're gonna do special moment frame system and intermediate moment frame system. You can see all the detail here. And then this is a fabrication, right? It's for the test specimen in the local precast factory. And then let's go. Yeah, we have to prove our connector have a good performance. So we applied a very large diameter reinforcement because we intentionally make a failure in the connector. So you can see our target load here, connector itself have a 1.5 times so-called 1.5 SY strength. That means connector always protected by addressing the over strength. And next one, yeah, we utilize the reinforcement here. If with smaller reinforcement there, the fracture always occur in reinforcement. We can obtain the beautiful stress strain curve of the this mechanical splice system. And then cyclic test also conducted. The slip is under control 0.3 millimeter. The second one is we intentionally debolting a little bit, just the help of bolting. Even in this case, just 0.44. That means the maximum threshold value is 0.3 millimeter. Quite good performance. Okay, and then compression to the tension test, that is really important to evaluate the slip. You can see the slip is very small. You can see the 0.14 millimeter. That is a really good the mechanical splice performance. Okay, this is a test result. The left side is dry connector only, and this one is dry connector plus hybrid connection. Let me show you. Yeah, the beautiful cyclic response you can see, right? So we evaluate the test result based on the ACI 371, the seismic connection for the non-monolithic connection. And then you can see The clear thing is the left side is a special moment frame system. So we address the large diameter reinforcement in the panel zone, and the beam reinforcement is smaller than that. So the fracture is always occur the outside of a plastic hinge. But the intermediate moment frame system, the fracture is occur in the bolted connection itself. I mean the reinforcement. That is, we have to protect it. So high seismicity region, we can protect the panel zone by utilize the very large, strong connector. And in the intermediate level of the seismic zone, for example, Korea, you can see that there is some substantial seismic damage in the panel zone, but it's okay for our region. Okay, you can see the strain measurement. Intermediate system, the yielding is a penetrate inside the panel zone. You can see the clear yielding is a penetrate inside the panel zone. But then you can see in the special moment frame system, the yielding is restricted inside the panel zone. That means all the plastic hinge always concentrate outside of the panel zone. That means a beam plastic hinge mechanism is developed, and we can control this one. So I proved that one based on the seismic test. And the column foundation is quite similar with the previous test, but all the reinforcement is connected by the dry connector. And right side, we can take advantage of some economical aspect of the grouted sleeve. So those 8 reinforcement is just a grouted sleeve. I will do it later, okay? In the construction site, we just fix the corner 4 and then go the next floor. And then some guys will follow the grouted sleeve in the next day. Just a quite good strategy to facilitate the construction speed. Yeah, this is a fabrication something. Let me share the video clip there, so you can visit my website. You can see this one. Okay, we have a limited time. So we utilize the DIC method. So we measuring all the deformation by using the visual the inspection right there, and then cyclic load until the 5% drift. There is nothing happen. It's a really great performance. So this is all the reinforcement is connected by the dry connector. In this case of almost 5% drift strength degradation happen. It's quite good. According to ACI special. The special moment frame requires a 3.5% drift and then 50% strength loss. This is much higher than that one. And then this is a hybrid connection, also shows the good performance. And then you can see all the failure and the response is quite similar. This is another damage. We intentionally remove the grout after testing to show you. Okay. And then final stage here. Okay. So far, I explained about the prescriptive design. Let me finish in 5 minutes. Okay. So this is the ordinary intermediate special system. But now it's the time to the performance-based design. Our target is emulative. So that means key to successful application of the seismic design is just the mechanical splice. For example, grout sleeve or mechanical splice. That is key. So we have to invest a lot of focus to the reinforcement connection. So we just do some dynamic analysis by using the Performance 3D, and this one is, you can see this is a poor energy dissipation, and this is good, the emulative precast connection. The maximum drift 2.5, and this one is at 6.0%. That means magnify the drift performance by the energy dissipation capacity. Okay, let me go. And this is my model for the ISO 7 something like that. Anyway, I proposed this one, the ISO under discussion with some panels. Okay, anyway, mechanical splice sleeve, we can address that one in the stiffness of reinforcement. So stiffness reinforcement decrease when applied the sleeve increase. So we can model sectional response like there. And then we make some energy dissipation model based on the existing all the test data we collect and try to make it this function to make this hysteristic. Yeah, sorry, hysteristic. This is a rule, okay? Sorry. Yeah, I'm not native speaker, sorry. Okay, so we can do the validation of the existing test of this cycling model, and then this is the Peiko China conduct a two-story, multi-story Peiko system test in Tongji University, the Professor Dai's previous job place. And we conducted this one, and then we calibrate this test. This is a static test. We conducted this the validation, our model, by using the OpenSys platform. Then we utilize this one, and the earth-scale record is utilized to apply this one, and then this is an analytical result you can see. If the connection have no slip, that means that this is a reinforced concrete, and 0-point slip, there is an emulative system, and 0.6 maybe semi-emulative system not allowed by the code. This 2.4 millimeter slip is a maximum observation according to my test of the existing mechanical splice. You can see the peak response is magnified, and then finally you can see some earthquake is I intentionally select a tricky earthquake, and then you can see the response is magnified twofold. Just a reinforcement mechanical slip, just a 1.3, 1.6, 1.2, 1.2, 2.4. This small slip between reinforcement make a disaster like this way. So this is my presentation, and then thank you for your attention today.